Okay, welcome to this session. My name is Rahul Pandit. I am the chair of the session. It's a great pleasure to introduce Guido Boffetta, who will tell us about turbulence and vortex dynamics in 2D fluids. As all of you know, he is one of the great authorities in the subject, so it's wonderful to have you here, Guido.
Thank you, Rahul. Thank you very much. So I was asked by the organizer to give an introduction to two-dimensional turbulence, so I thank them for inviting me, and I apologize with all the others because it will be a little bit off topics in this conference, but I hope it will be somehow interesting. So this is a brief kind of outline. I will discuss the phenomenology of two-dimensional turbulence, large-scale motion, how this phenomenology appears in three-dimensional flows, and then a very more recent part on the effect of boundaries. So I don't need to motivate you about studying two-dimensional system in general, and Navier-Stokes in two-dimensional are the simplest model probably that you can think of for describing the motion at large scale of the atmosphere and the ocean, in which not only the confinement, but also the rotation and stratification contribute to suppress vertical motion. I will not discuss here about stratification and rotation, and there are also some experiments in the lab that you can do to study two-dimensional turbulence. This is one of the simplest one based on soap film. So one slide about three-dimensional turbulence. We already seen this slide, similar slide yesterday. So the turbulence is a far from equilibrium system in the sense that you inject and remove energy at very different scales. Okay? And so between these two scales, you have what is called the Richardson cascade, in which the energy injected again at the injection scale, at the large scale, is unstable because a nonlinear term is transferred to smaller and smaller scale and eventually reaches the viscous scale, in which is removed by viscosity and transferred into heat. So in the implicit limit, so viscosity is 0, the energy is conserved, kinetic energy, but then it's dissipated by Navier-Stokes at a rate which is proportional to the entropy. The entropy is the vorticity square. And so the most important, probably empirical law of turbulence is what is called the dissipative anomaly, which means that when the viscosity goes to 0, the energy dissipation rate do not vanishes, but reach a constant value, epsilon. And this means that the entropy, because of the vortex stretching term that we heard about that yesterday, the entropy grows to compensate the decrease of viscosity and reach a stationary limit, steady limit for the limit of infinite Reynolds, which is equivalent to viscosity going to 0. So in two dimension, it is very different because in two dimension, you don't have the vortex stretching term. The vorticity, which is a scalar, is simply transported by the velocity, dissipated. I had also in the equation a forcing to reach a stationary state. And this is a linear damping. We represent essentially the interaction of the flow with the three-dimensional world. So for example, we represent the friction on the bottom of your container or the friction induced by air. It depends on the system you have in mind. And so in this system, not only the kinetic energy, but also the entropy is an implicit invariance. And so in the viscous case, you have a balance not only for the energy, which is the same as before, as in 3D, but also you have a balance for the entropy, which is dissipated at a rate which is proportional to this quantity, which is called entropy, but it's not very important. And so it means that in the limit of vanishing viscosity, large Reynolds number, the energy cannot be dissipated because the limit goes to 0, because the entropy cannot grow. Okay? So there is no dissipative anomaly in 2D. This was already recognized by Taylor, apparently 1 century ago, but Taylor concluded that there is no turbulence in 2D. And this is, of course, is not true. The point is that the energy is transferred not to small scale, but to large scale. This was already recognized many years ago by Fjordhoff. That is okay, this is the energy balance written now in Fourier space. So this is time derivative, the transfer term which correspond to the nonlinear terms and viscous and forcing. And then the nonlinear transfer term, which is written in terms of Fourier transformation or Fourier transform of the velocity field, because of the energy and entropy conservation, must satisfy these two equations. And so from these two, you can, if you take 3 wave numbers in Fourier space separated, so K correspond to large scale, intermediate scale, and small scale P, you can easily show that the rate of transfer from energy from Q to K is faster than Q to P. So it means that the two-dimensional Navier-Stokes equation will transfer more efficiently energy to large scale instead to small scale. So this is the idea. It's not true there is no turbulence, but the turbulence is qualitatively different than in 3D. And then there was the work, the famous work by Krajcand, where they extended essentially Kolmogorov work in 2 dimensions, starting from a paper in 67 and then several other papers. So if you take the energy balance, the Fourier space in stationary condition, and then you consider scale which are very far from the dissipative scale and the forcing scale, you can neglect all this term, and you add that essentially the integral of the transfer term, which is what is called the energy flux, or the integral of this quantity, which is the entropy flux, you can rewrite in terms of the energy spectrum. Okay, it's very standard, some kind of dimensional computation also, and then he ends with a prediction that for scale larger than the forcing scale, you assume to have a constant flux of energy, and you get this prediction for the spectrum, which is exactly the same as Kolmogorov did for 3D. And at small scale, you assume to have a constant flux of entropy, okay, which has a k squared with respect to this one, and so you get a different spectrum k to the -3, which is the new prediction. So the idea, the Krajcand picture of the double cascade is that if you inject energy in a system, in a 2-dimensional system, and the intermediate wave number, you have an inverse cascade of energy with this scaling exponent, and a direct cascade of entropy with a k to the -3 prediction. Okay, then there were some, in a paper by 71, Krajcand proposed a correction to this direct cascade, a logarithmic correction, because otherwise the flux is not exactly constant, but this is just the details. So the double cascade picture being verified by also some laboratory experiment. In the lab is very different to see both the cascades. What is also different is difficult to force the system at very small scale. So there were some experiments more recent in which very smart experiment where they force the system by Faraday wave instability. So you can naturally force at small scale, and they were able to observe the very clear inverse cascade. But probably in 2 dimensions, it's better to do simulation instead of experiment. At least I do simulation. And so this is the evidence, if you want, the double cascade scenario in a set of numerical simulation we did many years ago in collaboration with Stefano Musacchio. And so the idea is that we force the system at the intermediate scale, 100 in the simulation. So at larger scale, you see that there is a very clear k to the -5 term scaling. And then at small scale, you have a scaling law which is steeper than the prediction by Krajcand, but increasing the resolution, so increasing the Reynolds number, you see that the correction, so if you fit this slope, you get a correction delta with respect to the prediction, and this correction vanishes apparently, so it seems to vanish as the viscosity goes to 0. So in the limit of infinite Reynolds number, this suggests that we recover the Krajcand prediction of the double cascade with 2 simple scaling exponents. And so what I plot here are the flux of energy at the entropy. So there is a negative flux of energy, which means inverse cascade at larger scale, and a direct cascade, positive flux of entropy, which means a direct cascade at small scale.
Is there friction in this?
Okay, good question. Not in all the simulation. For E, I don't think we had any friction because it's so large that it takes a lot of time to reach the stationary state, but in any case, it's quasi-stationary system. And so some more details about the statistics of the inverse cascade. The inverse cascade is also different because, with respect to the 3-dimensional direct cascade, because we don't see any intermittency in the sense that if you compute the higher order statistics, what is called the higher order structure function, velocity difference to the power p average, you get that the scaling exponents are compatible with the simple scaling predicted by Kolmogorov, which is not the same in 3D. In 3D, you probably know there is intermittency. There are intermittency correction, the velocity fluctuation are very close to Gaussian, and also there is an interesting result, but I don't have time here to discuss that vorticity cluster in the inverse cascade are not only scale invariant, but they are also conformal invariant, but this is another talk. So what I want to discuss now is what happened to this energy cascade to large scale. So since we are injecting energy in the system, and the energy is not dissipated, the energy accumulates. Go to large scale, and at a certain point you reach the scale of the box, and they start to accumulate at the scale of your box, okay? You can see in the Fourier space, for example, so this is the energy spectrum as a function that evolves in time from the simulation. So this is the forcing. You see there is a flux of energy that moves the energy to larger scale, and eventually you reach the larger scale in the system, okay? You can also estimate what is the time it takes, very simple. And when you get this, the larger scale, the energy starts to accumulate and produce what is called the condensate, which has probably nothing to do with Bose-Einstein condensation, but I use this name, not invented by me, because it's the only connection I have with this, probably with this, most of you. So, and this has been observed not only in numerics, but also in the experiments, okay? This is a spectrum from a laboratory experiment, which they observe this bump in the Fourier space. But what is the condensate in physical space? This is much more interesting. So I have a movie of, this is a simulation in which we produce the condensate. So this is time 0. What you see here is just the forcing, which is at this small scale. Oops. Sorry. Okay. Now, the system develops small scale vortices, okay? And the vortices move with the velocity. Okay, this movie is a little bit smooth because of the connection, but in any case, what you should observe is that the vortices remain on the scale of the forces. But what is growing is the collective motion of the vortices. You have velocity that correlate on larger and larger scale because of the inverse cascade. Okay, so the movie is very long. So let me cut it. Okay, here is much better. Sorry. Okay, and eventually, when you reach the integral scale, the energy reaches the integral scale, you see that the condensate appears as two collective motion, two big vortices, which rotate in the opposite direction. Okay, so there are two elliptic points, if you want, here, and there is, you cannot see here, but from the movie, so very clear, you have an hyperbolic point in between. Okay, so this is how the appearance of the condensate appears in the physical space, vorticity field in particular. This particular case. And so this is not universal. There is a zoology of condensates because it depends, for example, on the boundary condition. In the experiments, in the simulation, we have periodic boundary conditions, so the average velocity must remain 0. The average vorticity is 0, so we have positive and negative vortices. While in an experiment, typically you observe a monopole, so there is a symmetry breaking between positive and negative vorticity. And then even in periodic boundary condition, if you have not a square box, but you have some aspect ratio, you get something different. So there is all a full phenomenology of zoology, you would say, of condensate, which has been studied. But there are also some universal features that I want to discuss because it's interesting. It is the structure of the vortex. The structure of the vortex is determined not by the boundary condition, but by the equation of motion, by the Navier-Stokes equation. So we can hope to observe some universality in this. And indeed, this is the case. And the computation, okay, I will skip the details, but very simple. You simply start from the momentum and the energy balance in stationary condition, written in a polar coordinates around one vortex, which is very natural. Okay, so you have a polar velocity, average polar velocity, the radial average is 0, of course. And then the point is that it's the nonlinear equation, so you have the usual problem of closure, which is typical in turbulence, but now you have a small parameter, which is the ratio, the fluctuation over the mean flow, the mean rotation of the vortex. So using this small parameter, you can close this equation, and you end with a very simple prediction for the vorticity profile in the condensate. So which is 1 over R with a coefficient in front which is not free. Okay, epsilon is the energy flux and the alpha is the friction terms. So there are two parameters that you can control. So there are no free parameters here, and this fit works very well. So these are the profile, vorticity profile computed in one of these guys. Okay, for different simulation with different epsilon, different alpha, and when you rescale according to this prediction, you get a very good collapse. Okay, but I want to remark that it works only in the core, far from the boundary. So this is 1/10 of the box. Okay, after that we observe deviation because this depends on the details of the system. Okay, but at least the core.
You have only the small vortices that are at the scale of the forcing, and then these big vortices are just balance.
Exactly.
And nothing in between. No other vortices of intermediate size.
Vortices not, but velocity, yes, of course, you have a scaling law for the velocity field. But if you look at the spectrum of vorticity, the spectrum of vorticity is peaked at the forcing scale because k to the minus 5 third times k squared peak a small scale, and then you have another peak, which is the condensate. Yeah, exactly. Okay. Okay, so far I discussed two-dimensional Navier-Stokes. Now I want to move to three-dimensional world. So how we can observe a two-dimensional phenomenology in a real three-dimensional flow. So there are several setups. Probably the simplest setup to study this problem is what is called the thin layer, which was proposed many years ago by Schmidt-Valeffe. So the idea is to have essentially a box in which one of the directions is much smaller than the other two. Okay, very simple. We still keep periodic boundary condition in all the direction for simplicity. So you have several scales in the system: the viscous scale, the horizontal scale, and we fix the forcing scale somewhere in between. And then it's clear that when the thickness scale is smaller than the viscous scale, everything, all the vertical motion are dissipated by viscosity, so we end up with in a two-dimensional Navier-Stokes, like in subfin, for example. Okay? On the other hand, if the thickness is larger than the forcing, you have a system in which you are injecting energy in a three-dimensional environment, so there is nothing that prevents the energy to perform the direct cascade. So in this limit, you expect to have 3D phenomenology. And what is interesting is when the thickness scale is between the viscous and the forcing scale. So we introduce this thickness number, defined in this way. And so we want to understand how is the transition between 2D and 3D phenomenology as a function of, as you increase S, as you increase the thickness. Okay, so because the different phenomenology is the presence of the inverse cascade. In the inverse cascade, the energy is transferred to large scale. The easy way to observe an inverse cascade is to look at the total energy in the system. If the total energy increases in time, it means that you have an inverse cascade, otherwise not. So these are the results from simulation for different thickness, okay, of this thin layer. And you see that indeed, if the thickness is sufficiently small, you have that the energy keeps growing. Okay, so it means that there is a transfer of energy to large scale. But this transfer is reduced as you reduce the thickness, you increase the thickness, and eventually when you reach this number 1/2, a magic number, you have that the system reaches stationary state, which means that there is no inverse cascade anymore. So this is an indicator of the transition between 2D. So you can take the slope of this line, and so this gives you the fraction of energy that goes to large scale, which is 1 when you are exactly 2D, and goes to 0 when S is equal to 1/2. But what is interesting, there are intermediate values of thickness in which part of the energy goes to large scale and part of the energy goes to small scale. So you have what is called the split cascade. And so you have the two phenomenologies together, 2D and 3D. How is possible? So let's concentrate on this particular value, S equal to 1/4. And if you look at the energy flux, okay, so we have seen before, so we are injecting energy in this way number. There is an inverse cascade, which about 25% of the energy flow to large scale with the inverse cascade, but the other 75% goes to small scale. So you have double, not in the sense of Keynesian, a split cascade, both inverse and direct for the energy. And if you look at the spectrum, in this situation, the spectrum is very small because, okay, this is what the spectrum looks like. You have the forcing here, the inverse cascade with the with the Kreiker 5/3. Then here you have the direct cascade of entropy with k to the -3. But then when you reach the thickness scale, the flow becomes three-dimensional. So from this to this viscous scale, you have another k to the -5/3. But this is 3D cascade, direct cascade. This is 2D inverse cascade. It's very simple at the end. When you see it, you understand. There is nothing strange. Okay, then, okay, one point, why we have this phenomenology at large scale? The simplest, one possible explanation is that because we have seen at the beginning that the fact that 3D and 2D are different because of the different number of Vichy invariants, so in 2D we have also entropy, the idea is that maybe there is this thin layer, there is a suppression of the vortex stretching term, which is responsible for the entropy production. No? Which is it means that even if the equation is different, because the three-dimensional equation is different from 2D because of the presence of this term, it is possible this is suppressed at large scale dynamically. So what we compute is the contribution to the entropy fluxes from these two terms, which is, this is the transfer, which is responsible for the transfer of entropy, which is also present in 2D, and this is the entropy production term. And this is the result from the simulation. So in blue, I plot the entropy flux, and in red, the entropy production. So this is the forcing scale, this is the thickness. So this range corresponds to the range here, which we observe the direct cascade of entropy. And indeed, we observe that here, in this region, the entropy production is suppressed, dynamically suppressed, it doesn't exist. And then when you reach the confinement scale, the entropy production, and you have a constant flux of entropy because you don't have production. But then the production starts, and so you don't have a constant flux of entropy, this becomes three-dimensional. Okay, so this is the very simple idea. Okay, the last, how many minutes? No, this is for 40, I think, but
is it for 40?
5 minutes. Okay. I want to mention more recent work about the effect of boundary, because so far I consider only no boundary condition, periodic boundary condition in all the direction. And the confinement is simply the fact that you don't have available wave number at large scale in one direction, okay? But now what happens if you introduce some physical boundary? So it's work done in collaboration with Marco Rosti, Noist, and Stefano Musacchio. And so we consider now a setup which is again a thin layer, but now with a no slip boundary condition on the bottom and a free slip boundary condition on the top. So it is similar to what they do in the experiment in the lab. Okay, you have a small tank of water or any liquid, whatever you want, and then we force the system at a given wave number, which is about the size of these vortices. We consider different thickness, okay, between 0.03 and 2. So we change the vertical resolution. And the forcing is always white in time and two-dimensional. So we expected, so it was a little bit surprising because we expected in this system a similar phenomenology that before. So we look at how the energy grows in time. And this was a little bit disappointing at the beginning, because we found that the energy that you remember it should grow in time if you have an inverse cascade. We observed that at the beginning we observe a growth of the inverse of the energy, so it means an inverse cascade. This is for S=114 that correspond to the simulation we had discussed before without boundaries. But eventually the energy is dissipated and reaches a stationary state. And this is true for all the thickness that we study. Okay? We were unable to observe an inverse cascade at long time. Stationary condition. Everything is transient. So if you look better at already at the level of the picture, you see that there are very big differences between the bottom layer and the top layer. So the bottom you have some small scale structure. So we decide to compute the spectrum, the energy spectrum on different slices, horizontal slices at different depths. Okay, and so this is the result at a given time, which is correspond at the time of the transition. And what we observe is that close to the bottom, you have a spectrum which is very close to Kolmogorov spectrum 3D. While close to the surface, which is this black line, where this grows, theta grows in this direction, close to the surface, you have a spectrum which is much, okay, then you have dissipation, but here you have a spectrum which, if you believe, you have a scaling law, which is much steeper, close to k to the -3. So the idea that you have a simultaneous presence here in physical space of three-dimensional flow close to the bottom because of the boundary condition, and a two-dimensional light flow close to the top. But then this propagates in time. As you can see, these are the spectra computed at different time. So at the beginning, this is close to the top surface. At the beginning, you have a spectrum which is close to k to the -3, but then you have a transition, and eventually you reach at long time a spectrum which is close to Kolmogorov direct cascade. So the idea at the end is very simple. You have a three-dimensional turbulence. We start at the bottom because of the boundary condition, then propagates in all the domain, and eventually you get a three-dimensional flow in the system. And not a small scale? Yes. Yes, good question, because we were not sure what we could observe. So we forced at the wave number 8 in order to have both the cascade more or less resolved, because the resolution here is not huge, it's 2000 square or 4000. But in any case, if you do the same simulation without boundary condition, you see very clear the inverse cascade. Okay, you don't see the scaling, but you see that the energy keeps growing, and you see all the phenomenology. So this is really induced by the force, not by the force. So the similar consideration, if you look at the flux, these are the fluxes at two different times. A short time in the red, you see the inverse cascade, so a negative flux at large scale, but this is suppressed at a long time, it's close to 0, and everything goes to small scale. So, okay, so this is the end of the talk. I don't have a general conclusion, it's a small conclusion for this last part. that we found that in presence of no-slip boundary condition, we were unable to create an inverse cascade which keep in a stationary state, I mean, for a long time, because we have a three-dimensional propagation from the bottom. So I want to mention this is only partially consistent with laboratory experiment because people were able in the experiment to generate the inverse cascade. They studied two-dimensional turbulence, even in presence of real physical boundaries. So, but there are some important differences because most of the experiments are done in with two layers of fluid with different density, and most of the time also immiscible fluids. So this makes, in some way, decouples the upper layer with respect to the bottom. And also the forcing is very different from what they are doing. So we want to do some further comparison with experiment in condition more closer to experimental condition. So if you want some more details, and so thank you very much for your attention.